In this presentation, we will study Programmable Array Logic (PAL). We have already completed our Programmable Logic Array (PLA), and it is very much possible that you have been directed here from that lecture only. People were asking me to make the presentation on the PAL, so here it is. Before going to the presentation, I would like to mention some points. The first thing is that it is very much favorable if you have already learned about the PLA. It will help you in this presentation. The another point is that if you look into your book, Morris Mano or any other book, you will find that they have made some tables, and according to me, I don't feel like any table is required to understand the PL. It is just wastage of time. So I would like to keep this presentation as small as possible, as simple as possible, and as effective as possible. So let's move to it without wasting any time. So the first point that you can see is it is most commonly used PLD, the programmable logic device. It is most commonly used. Why it is most commonly used? Because it is having the fixed OR array. If you remember, in PLA we were having the programmable AND array as well as the programmable OR array, but in this case we don't have the programmable OR array. There is one advantage of the fixed OR array, which is the simplicity. We don't have to worry about programming the OR array, so it is very simple. But there is one disadvantage, and it is the flexibility. The flexibility of the PAL is not as much compared to the PLA. So you can see here, this thing is the PAL, a common structure of the PAL, and actually this is the last step that you have to do in the problems of the PAL, but I have made it to just give you a feel that what is PAL. We will do a stepwise solution of the PAL. First, I will explain you something in this structure. You can see there are three AND gates, this one, and this one, which is fixed to this OR gate. This dot shows that it is fixed. You cannot program it. You cannot break this connection. This 3 AND gate is fixed and connected to this OR gate. Similarly, the last 3 AND gate is fixed and connected to this OR gate. On the other hand, if you see the input to this 1, 2, 3 and 9 AND gate is programmable. You can connect it to A complement B, B complement C, or C complement. Fine, like we did in the PLA. So let's move to one problem, and stepwise we will see how to solve the problems in the PAL. Here you can see we are having X, Y and Z, which are the three outputs, and the min terms are specified. So actually the first step is to see the min terms. You cannot make this structure without looking to the min terms and minimizing it. This structure is the last step, as I have told you. You cannot make this structure first. So the first thing is look to the min terms. So for X, the min terms are 2, 3, 5, 7. For Y, it is 0, 1, 5. And for Z, it is 0, 2, 3, 5. The next step, you already know, is the minimization. You can do the minimization by using the K-map. We are not going to do the K-map minimization here because we don't have that much time. I have already minimized these things. So let me write it down. For X, when you minimize it by using the K-map, you will get A complement B or A C. For Y, when you minimize it, you will get A complement B complement or B complement C. And for Z, when you do the minimization, you are having A complement B, A complement C, or A B complement C. So this is the second step, the minimization. The first step is to see what are the min terms, put it in the K-map, do the minimization and see the results. Once you have these results, it's time to make your PAL. So the first step in making the PAL is looking for the number of variables, and in this case we are having 3 variables A, B, C. So depending upon these variables, we will make the input buffers. So we were having the 3 variables A, B, C, so we made 3 input buffers. You already know what are the input buffers. It's nothing but a combination of NOT gate that gives you 2 outputs. The one is the non-complemented form, another one is the complemented form. Okay, here I am having A, and at this point I am having A complement. Similarly for B and C. So once you are done with your input buffer, it's time for the AND array. Now the number of AND gates will be decided depending upon the minterms. In the first case, I am having two minterms, a complement b or ac. In the second case, again I am having two minterms, but in the third case I am having three minterms. So remember, whatever the highest number of minterms, we will take it. In this two case, we are having two minterms, and in the last case I am having three minterms. So I will take three minterms, and I will make three AND gates for each. Okay, it's not like the first two cases are having two minterms, so I will make two AND gate. No, I have selected three, so I will make three AND gates for all the cases, and three times gives us 9, so I'm in total having 9 AND gates. And what is the number of OR gate? It is the number of output x, y, z, 3 outputs, so 3 OR gates. As you can see here, 3 OR gates. Fix the 3 AND gate to the OR gate, 3 AND gate to this another OR gate, and the last 3 AND gate to the last OR gate. It's time to do the programming of the programmable AND array. So what is our first output? X. It is a complement b or ac. So a complement is this thing, b is this one. So this AND gate gives us a complement b. The another thing was ac, so I will use this AND gate for that. At this point I am having a, and at this point I am having c. So this AND gate gives us a c. Fine, but you can see for the first output x, there are only two minterms. So what about this third AND gate? It will not be used. And how we are going to do that? We will use fuse. At all these junctions, or you can say points, we use fuse, F-U-S-E, fuse. This fuse, when intact, will make the points open. So all the fuses at this point, this point, this point, this and this will be intact. So none of the points are connected to this AND gate. Fine. Similarly, we will do for y. And for y, I am having a complement, b complement, or b complement, c. So this AND gate I will use for a complement, b complement. This is a complement, this is b complement. It will give a complement, b complement. And this AND gate I will use for b complement c. This is b complement, this is c. It will give b complement c. And again I will intact the fuses for this AND gate. Fine. Now let's move to z. For z I am having a complement b, a complement c, a b complement c. So let's do the programming. This AND gate will give us a complement, b complement. This is your a complement, this is your b complement, a complement, b complement. This AND gate will give us a complement c. This is your a complement, this is your c. And the last one gives us a b complement c. This is a, this is b complement, and this is c. So it is a b complement c. So we are done with the programming of our programmable AND array, and the outputs are x, y, z. So in this way we have to do the PAL. So you can see we have not programmed our OR array, but we have only programmed our AND array. So this is all about the PAL. You can do any problem, I guess. If you face any problem in PAL, you can definitely ask it in the comment box. So this is all for this presentation. See you in the next one.